In this video, we're going to compare linear versus exponential growth. So throughout your math career, you may have done a lot of work with linear expressions. The most popular thing we do is we have y equals mx plus b. This is the slope, and this is the y-intercept. I don't know why I just wrote that because it's right here. But we previously defined an exponential function, so this is different. Now the x is in the exponent of this expression. A is the initial value, that's where we're starting out, and b is the base. It's kind of the thing that we multiply by. So this is an exponential function, and if you see it compared to a linear function, big differences. Here, m is just multiplied by x, but here x is in the exponent. These b's are different thing. One is a base, one's a y-intercept, but different things are happening in exponentials and linears. But what exactly is happening? So let's plug in some values. So if I plug in 0 into this expression, I get 3 times 0 plus 2. That's 2. If I plug in 1, I get 3 plus 2. That's 5. Plug in 2, 6 plus 2 is 8. 3, 9 plus 2 is 11. 4, 12 plus 2 is 14. So we'll come back and look at these values in a second. In our bottom, this is an exponential. We get 2 times 3 raised to the 0. 3 raised to the 0 is 1, so this is 2. We get the same first value. The y-intercept and the initial value are the same. 1 is 2 times 3, which is 6. 2 is 2 times 9, which is 18. 3 is 2 times 27, which is 54. And 4 is 2 times 81, which is 162. So what's happening in between each of the steps? In my linear expression, every single time I increase x, I'm just getting another 3. So if we look between here, all I'm doing is just adding 3. So I could get the 5th stage by plugging in 5, or I could just add 3 to this and know the 5th stage is going to give me 17. In the exponential case, every single time I increase this exponent by 1, I'm just multiplying by another copy of 3. So you can see 2 times 3 is 6. 6 times 3, 18 times 3. 54 times 3. If I wanted to get the 5th one, again, I could plug 5 in, or I could just take 162 and multiply it by 3. What would that give me? I used to use a calculator. It's not as easy as adding 3. 486. Multiply by 3 again. So this is the major difference between linears and exponentials. They're very similar in the fact that they start with initial value and then do the same thing over and over again. The only difference is with a linear equation, we're adding the same constant each time. This is known as the slope. So that slope is the value we're adding each time we increase x. With an exponential function, we're multiplying by that same constant. So in that previous example, we had a 3 to the x. That thing we're multiplying by is 3. This is known as the base of the exponential. So the main thing you'll have to do for this lesson is identify if something is exponential or linear, and then write the formula. So if we identify it's linear, we would do that because we're adding each step. We're going to have our final answer in y equals mx plus b. If we figure out it's exponential, because we're multiplying each step, our formula is going to be y equals a times b to the x. So which one do we have in this case? To get from 7 to 2, I can subtract 2, or I can multiply by, 5/7 or something like that. Right away, you may not be able to figure out what I'm multiplying by. Chances are, 5 to 3, I subtract 2. 3 to 1, I subtract 2. Subtracting 2 is the same thing as adding negative 2. So this is going to be a linear equation. My final answer is y equals m is the slope. That's the constant I'm using here, so that's a negative 2. B is the starting value, 7. So that is my linear equation that represents this table of values. You can always check, try the final value. If I plug in 4, I get negative 8 plus 7. That's negative 1. So it does fit my table. This one, to get from 3 to 9, I add 6. To get from 9 to 27, I have to add 18. So automatically, this is not the same number, which means this is not linear. So we got to try multiplication. To get from 3 to 9, I multiply by 3. 9 to 27, I multiply by 3, multiply by 3, multiply by 3. So this is definitely exponential. I'm multiplying by the same value every single step, and my final answer is y equals a is my initial value, my starting value for y, times my base is the thing I'm multiplying by, raised to the x. All right, so that is my exponential expression for this one. Again, you could try, if I plug in 4, 3 to the 4 times 3 ends up being 243. Another example, I had to get from 64 to 32. If I'm trying to make it linear, I have to subtract 32. From 32 to 16, I have to subtract 16. So right away, I see that it's not going to be linear because these values are different. Linears add the same thing over and over again. So my other option is to do exponentials. Think about multiplication. How do I multiply to get from 64 to 32? You could think about it as dividing by 2. But dividing by 2 is the same as multiplying by 1/2. So if I multiply by 1/2 each of these stages, I get to the next stage, which tells me this is exponential. And my final answer is starting value times the thing I'm multiplying by raised to the x. All right, so that is my expression for this exponential data. All right, and here's one for you to try on your own. All right, take a second, figure out if it's linear or exponential, and then create the model, and I'll show you the answer in 3, 2, 1. All right, so why is this the answer? 8 to 11, I add 3. 11 to 14, I add 3. So I'm adding 3 every single time, tells me it's linear. That's my slope. And then, again, b is the initial value at the starting point. All right, so linear growth, they're always going to look like this. Exponential growth, they're always going to look like this. So these are kind of formulas you have to have memorized in a way. I mean, they come from mathematical properties, so they're not just like plop there. So not quite memorization, but for right now, I just know that these are the two forms you're looking at. If you're adding the same constant, that constant's going to go there. If you're multiplying by the same constant, it goes there.